Wednesday, we'll move into sets and maps. All right. Oh, yeah, that's right. Okay. So at the end of the last lecture, we did a dice rolling simulation, and we used a list to store the results. Here, I want to do something similar. This time, it's a coin flipping simulation. Oh, here we go. So again, I think for many of you, because of your engineering background, you may have even taken a stats course by now. You'll know the answer to this. So if you flip a fair coin n times, how many heads do you expect to see? Right. I think everybody knows the answer here is roughly n over 2 if it's fair. Right. Now, how often do you expect to see n over 4 heads? That's a little bit harder, right? How many times do you expect to see 1 head if you flip a coin 30 times, right? Most of you probably know the answer is not very many, but it does occur. If you've heard of the binomial distribution, then the distribution of the number of heads or the number of tails follows a binomial distribution. So what I want to do is I want to write a simulation that if you flip a coin n times, it basically counts the number of times you see 0 heads, 1, 2, up to n, right? So if you flip a coin n times, the probability will be proportional to the number of times you see 0 heads, right? Probability that you get n heads will be roughly proportional to the number of times you see n heads. So this is going to follow the same pattern as the dice rolling simulation, right? So if you're going to compute the odds via simulation, you can use the following algorithm. So I'm going to make a list, right? Now this list is basically going to count, right? It's going to hold the count of the number of times you roll n heads, right? So if I flip a coin n times. So if I flip a coin n times, right, I need a table having n plus 1 rows, right? So I'm going to make a list. I'm going to add n plus 1 zeros to the list, right? I'm going to repeat the following m times. So so I'm going to flip the coin many times, right? Each time I'm going to flip so I'm going to write a loop that flips the coin m times, right? We're going to choose m to be a large number, right? I'm going to set the count equal to 0. So the count is just the number of times you see a head, right? And now I'm going to repeat the following n times, right? So I'm going to flip a coin by using a random number generator to randomly generate true or false, right? If I get some value that corresponds to seeing a head, I just add 1 to the count, right? Every time I add 1 to the value at index count in the list, right? So here's my simulation. Step 2 is flipping the coin n times, right? After you flip the coin n times, you get some number for the count, right? So suppose you flip a coin 20 times and you see 5 heads, right? Then I'm going to add 1 to the value at index count in the list, right? And then I'm going to do the whole thing all over again, right? So I'm going to flip a coin n times, and I'm going to repeat that big M, little m times. To get the probabilities, I'm just going to divide each element of the list by m. Right. Okay, so rather than doing this in Eclipse like I did with so rather than typing it all in, I'm just going to show you the answer. So here's our little simulation, right? So I want to flip a coin 20 times, and I'm going to do it that many times. So I'm going to do it 1 million times. Right, so m has the value 1 million. Right, I've made final local variables. Right, so these represent constants. Once I assign a value to n and m, right, I can no longer change their values. Right, that prevents me from accidentally changing the value somewhere in here, right, which would mess up the results of calculating the probabilities. So I'm going to make my list. Right, I'm going to add n plus 1 zeros. Right, now to add n plus 1 zeros, right, using a counting style loop, right, you're going to start with the loop variable equal to 0, right? Now the loop variable goes up to and including n, right? So that becomes less than and equal to rather than just less than. Right, each time through the loop, I add the number 0 to the list, right? And that produces a list of n plus 1 zeros. The next part, I have to flip a coin n times. Okay? So to flip the coin, I'm going to use a random number generator. Oh, there's something I forgot to tell you. When you import this list, it's important that you import the list from java.util.ArrayList. Okay? So ArrayList, it's only in the package java.util. But a little bit later on in the course, instead of writing ArrayList on the left-hand side, we're going to switch to writing just list on the left-hand side. And it turns out that there's several list classes in the standard library. So in Eclipse, when you import or when you create a class, so I'm just going to quickly make a class that uses the list interface. Right, so here's my using list class. I just want to make a little method, so we'll do a main method here. So right now we're writing this all the time, right? So array list of string t equals new array list. Now when you write that, because I haven't imported the class, Eclipse complains, right? So you see the red array list is underlined in red. If you hover over it, it suggests some fixes, right? For array list, the first fix is normally correct, right? So you import Java util array list and everything's fine. When I tell you about interfaces, you're going to start writing this instead. Right, now this is a little bit different for, I think, most of you, right? So for most of you, and when you program in C, normally the type on the left, the type of the variable on the left-hand side, normally it matches the type on the right-hand side, right? Unless this is a void pointer. But anyway, that's another story. So here you can see that there's a problem, right? So if you hover over list, it says it can't be resolved to a type. So again, it's telling you that you need to import a class. You need to import the list, you need to import the file that defines the list interface. And if you look at this version of Eclipse, your Eclipse might show you something slightly different, right? It says import list from java.awt. Don't do that, right? That's not the one you want. So it's a different list class. There's the second one says import it from com.sun.tools.javac.util. Don't do that one either. You have to pick the one that imports the list from the package java.util. Right, so that's the one you want. If you import one of the other two instead, you'll get all sorts of funny errors. Let me get rid of that. Right, so for example, if I import the one from java.awt, right, it'll still say there's a problem. Right, so now it says the type list is not generic. It cannot be parameterized with argument string. Right, and that's because the list class that's defined here happens to be a class that is a non-generic class, right? And it's meant to be used for something else, right? So it's actually meant to be used with when you're building a graphical user interface. Right? So you have to make sure that when you import the class that you import the correct one. Right? It has to be the one from java.util. Okay, there's our random number generator. Right, now I need to simulate flipping a fair coin, which means I need to simulate flipping one of two values, right? And so Boolean always has one of two values. So to flip a coin, I can just do rng.nextBoolean, right? That will randomly generate true or false. And I'm going to use true to indicate that I've seen a head, right? So if when I flip a coin, I see a head, I'm going to increase the count by 1. Right, so there's my inner loop. I guess all of this here's this stuff here. So that part there simulates flipping a coin n times, right? And it counts the number of times that you see a head. Right. After that loop's done, you go into your list and you set the element at that index, right? So what do? I set the element at that index to whatever's there now, right? So to get whatever's there now, I use get, right? And you add 1. And that updates the number of times that you've seen n heads, right? Once all of that's done, so once you've run that 1,000,000 times, right, you can then go through the list. Now remember, the list is it just stores the number of counts, right? So if you want to convert those into probabilities, or you want to convert those into approximate probabilities, right, you divide each element in the list by m, right? Now, for those of you who've taken statistics, right, the cumulative probability, right, if I sum up all of the values, right, in the table after dividing by m, you know that you should get 1, right? So if you run this thing, sure, right? Okay. So what do you get? So let's see. Let me make this a little bigger. You know what? Let me. Where do I print it out? Oh no. Okay, that's fine. So that's the number of times you see 0 heads. Right. So it's not 0. It's small though. Right? In this case, though, the number of times you see 20 heads is in fact 0. So in our simulation, we never actually managed to roll 20 heads. Right. And if you go to the middle value, which will be at 11, so 0, 1, 2, 3, 4, 5, 6, 9, 10, 11. Or sorry, the middle value will be, so 10 and 11, right? 10, you want 10, right? Number of times. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you can see that is in fact the highest value, right? There's 9, there's 11, right? They're roughly the same, or almost the same. There's 8, and there's 12, right? They're roughly the same. There's 7, and there's 13. Again, they're roughly the same, right? So this distribution appears to be symmetric. And the total, right, or the cumulative probability is in fact very close to 1, which is a nice verification that we've actually done everything correctly, right? Because if we had computed the probabilities incorrectly for some reason, this number here would not be 1. Right? Were you able to quickly state what probability, what prob add, prob set, prob get means? Yeah, for sure. Oh, sorry, right here. Oh no, let me go back to the Eclipse. It's easier here. Okay, so this table, so that table is represented by the list called PROB, so prob, right? The index is just equal to the number of times you see, is equal to the number of heads that you see in a simulation, right? The probability is the value that I'm storing in the list. Okay. So each time I flip, so in here, so this inner loop here, this flips the coin 20 times. Right? After I flip the coin 20 times, I want to see how many heads I see, right? So that's count. Right? So in the list that I'm creating, right, I want to set, right, I want to add 1 to the value that's sitting at that position in the list. Right? So for example, suppose I saw 2 heads in my simulation, right? Then I want to add 1 to whatever value is sitting here, right? Because this value to begin with is going to be the count, right? The number of times that I see 2 heads, for example, right? The number of times I see 0 heads, the number of times that I see 1 head. So I want to add 1 to whatever value is sitting here, right? So how do I add 1 to whatever value is sitting there? Well, I need the value that's sitting there right now, right? So that's get. So get is get will get the element at that index. Add 1 to that value, right? Then I need to set that value back to the, I want to set 1 to whatever that value that is, right? So you use the set method. You set the list at that index to whatever value that is. Add back here. So prob add, so the add method appends to the end of the list, right? So here I've got an empty list, right? Here I'm going to append a 0 to the end of the list each time, right? So if you run the program. So you can come into the program and fiddle around with the program, right? So if I come up here and then I just print out the list. So this is one of the nice things in Java, right? Compared to C, right? I can actually print out a list, and I don't have to like write my own loop or function to do so, right? If I simply send the list to the println method, it'll automatically print out the list. So I'm going to print out the value of I plus prob. Okay, now notice this gives you a problem. This indicates a problem. Right? It would be nice if I could write this, because I want to write out the value of I. Right? So I want to print out the loop variable, and then I want to print out what the list looks like at iteration I. But I can't do that. So the reason you can't do that is because that's an int and that's a list, right? So I can't do that. So I need to make one of these a string, right? So why don't I do this instead? So I'm going to print out the value of I. I'll append that to the string space colon space and then print out the list, and that works fine. So when I do this, you'll see how what add is doing. Right. So when I do that, right. So after the loop run once, there's 1 0. Right. It runs twice. There's a second 0. It runs 3 times. There's a third 0. Right. So add simply adds to the end of the list. So if you go into this program and play with it, don't print out the list here, because this runs a million times. So you're going to get a bunch of stuff printed out here. Right. If you do that, change the value of m. Okay. So for example, you decide to do that, come back in here and change the value of m. So we'll do this 10 times. And now you'll see. So here we go. Right. So the first time we run the program, it looks like we saw, I don't know, about 10 heads. Right. You run it again. That went up by 1. Again, that went up by 1. Sorry, this one went up by 1. Right. And so on and so on and so forth. So you can always run the program, print out the intermediate results to see what's going on. All right. Any other questions? Okay. Now this is a simulation, so there is an aspect of randomness to it, right? So the probabilities that you get at the end, they're not exact. If you run the program again, you'll get slightly different numbers, right? So even with 1 million, right? So if you run the program over and over and over again, the probabilities that you get will be slightly different each time, right? As the value of m increases, the closer and closer and closer you'll get to the to the expected probabilities, right? So the closer and closer you'll get to the actual values you would get if you computed the values from the binomial distribution. Okay? So when m is very small, you're going to get very poor results, right? You'll get results that aren't very close to the binomial approximation, to the binomial distribution, sorry. As m grows larger and larger and larger, you'll get better and better. You'll get better and better results, right? So in real life, when engineers and scientists run simulations, right, they tend to run them many times. Yeah, so we'll just leave it at that. All right, let's look at a different problem. So this one's a very different problem compared to the 2 that I just solved, right? Compared to the coin flipping and to the dice rolling simulation. I should just quickly ask, have you seen recursion already? Because otherwise this is gonna not be very useful. You must have, did you not do any recursion in your data structures course? You must have seen some recursion in your data structures course. Yeah, I think so. I can't imagine them teaching you that course without doing recursion. Has anybody not seen it? I guess that's a better question. Okay, so it looks like you did see it. All right, so here I'm going to use recursion on lists. So here's a little problem. It's a little toy problem, but it illustrates it's a very good example of why you might use recursion as opposed to iteration. Right, so here I've got it's basically this little game that you can play, right? It's not a very good game, but it's a little game that you can play, right? So Jump It is this game where you start at the left-hand side, right? So you have this board, and it's just a straight line, right? So I can represent the board's represented as a list of integer values, right? The left-hand square is always 0, right? And every other square contains a positive integer value. So it's strictly positive, so 1 or greater. You want to start here, and your goal is to reach the right-hand square, right? On each move, right? So starting here, I can move 1 square, right? So I can move to the 3, or I can move 2 squares, so I can move to the 80, right? And you can do this every time you move, right? The square that you land on, that's the cost of landing on that square. Right? So if I move 1 square over, the cost is 3. If I move 2 squares over, the cost is 80, right? Your goal is to reach this square with the lowest cost, right? So I want to reach that square with the lowest cost. This list can be arbitrarily long, right? So in this little toy example, it's fairly easy to work out what the lowest cost is. But if the list gets very long, it suddenly becomes not so easy to do if you try to do it by hand. Okay, so here's a solution for the example. Right, I move 1 square, so that's cost of 3, and then 6, so that's 9, and then 10, so that's 19. Right, so I claim that that is the lowest cost solution. Now, to get the solution, right, you might think that, well, there's a 3 and an 80, right? So obviously I'm going to go to the 3. Right? Now I can go to the 80 or the 6, so obviously I'm going to take the 6. Now there's a 57 and a 10, so obviously I'm going to take the 10. So in other words, I'm going to choose the step that leads to the lowest cost square. Right? Lowest cost is 3, lowest cost is 6, lowest cost is 10. Right? And so the answer is this, do you always get the correct solution by moving to the square with the lowest cost? Right? The answer is no. Right? Why is it no? Right? So it might, because it might be better to move to a square with a higher cost, because you would have ended up on that square anyway. Okay. So this is an example of a greedy algorithm, right? What I just described here. This is a greedy solution to the problem. I want, right, always move to the square, always choose the next square with the lowest cost. So for example, right, somehow I've gotten to this square here. Right, now I'm going to choose to go to the square that always has the lowest cost. Right, so I'm going to go to the 1 instead of the 5, right? Then I'm going to go to the 5 instead of the 6. Then I'm going to go to the 1 instead of the 6 again, right? So my cost here is going to be, well, 17 plus 1 plus 5 plus 1, right? That's 24, right? Now the problem is right here, right? I moved to the 1, but I could have just moved to the 5 anyway, right? So it turns out your lowest cost strategy is, in fact, to skip the 1 and go to the 5, right? And that gives you a cost. Right? All right. Now, to solve this problem using a loop, for example, right? You're basically what you would end up doing is you would have to. So the brute force solution would enumerate every possible set of moves, right? And then you would loop over all possible sets of moves. Right. So in other words, the brute force solution would look at the cost of moving 1 square every time, right? And then it would look at the cost of moving 2 squares and then 1 square every time, right? And so on and so on and so on and so on. And you have to enumerate every possibility, right? Now, because you can move to you always have a choice of moving to 2 squares, right? So this is roughly, this is exponential in the number of moves, in the number of possible moves. Right? So you'd have to enumerate that many different sets of moves, right? And doing so with a loop is not exactly obvious how you would do that. Right? Okay, let's see. So I want to solve this problem instead using recursion. because the recursive solution turns out to be surprisingly compact. So to solve a recursive problem, right? Remember, you need to define your base cases. So when do you know the answer to your problem, right? And you want to define your recursive cases, right? So how do I make the problem smaller, and then in this case use the method that I'm writing to solve the smaller version of the method, right? So remember, in recursion, you need somewhere to stop. That's your base cases. You want to make the problem smaller at every step, so that you and you want to make the problem identical to the same problem that you're currently solving. You just want a smaller version of that problem at every step. And that lets you call your recursive method over and over and over again to solve the problem. So how do I know that this problem is solved? Right. So you know your problem is solved when you can write down the answer, right, to the problem. So if your board size is 2, right, you know that you're done because you have no choice of your next move, right? So if your board size is 2, the only solution is to move to the next square, right? Your total cost, well, that's just equal to the cost of the square you're on, right? Plus the cost of the square that you're going to move to. Similarly, if your board size is 3, you're also done, right? Because you would never step to the second square, right? You would never pay the cost of moving to the second square. You just jump to the final square, right? So your total cost is the cost of the square you're currently on, plus the cost of the final square. Whoa, sorry. Right, so there are your 2 base cases, right? Those are the 2 cases where you know the final answer to your solution. Right, now you could include more base cases if you wanted to, right? So you could in fact write the base case for the size when the size of the board is 4 and 5 and 6 and so on, right? It's technically possible to do, right? But when you write a recursive solution, you don't bother to do that. You just let the recursion find the solutions for any board size bigger than 4, right? That's the point of using a recursive method. So there are my base cases, right? So first of all, here's my method. So I'm going to write a method called cost. Right? My board is just a list of integer. Right? It returns the total cost. It returns the minimum cost of solving that board. So if my board size is 2, right, I know that the total cost is just the sum of the 2 squares. Right. If the board size is 3, then I know that the total cost is just the sum of the first square and the last square. Right. All right, now what about the recursive cases? Right. So for the recursion, right, to solve a board, right, you know that you're always going to do one of 2 things. Right. Either you're going to take, so starting from the first step, right, or starting from the first square, you're either going to move 1 square or you're going to move 2 squares, right? Those are your only 2 possible solutions, right? So how do you compute the cost of moving 1 square? Right? So if this is my board, so ignore everything over here. So if that's my board, right? Then when I move 1 square, right, I just need the cost of the rest of the board. Right? The rest of the board is just a smaller list. Right? Here's the list of size 5. Right? Move 1 square, I now have a list of size 4. If I move 2 squares, so I go from the 17 to the 5, right? Then I just need the cost of navigating the rest of the board, right? So that's a board of size 3. Right? How do I represent that board? Well, that's just a sublist of the original list. Similarly, that part of the list, well, that's just the sublist of the rest of the list. And our array list class has a method called sublist. So why don't we just use that? So this is the complete algorithm to solve this problem, right? So if I'm going to take 1 step, right, what does the board look like? Well, my board, right, is just the sublist of the current board, right? Starting at index 1. Right? So in other words, ignore the square that I'm currently on, right? I'm currently on the square at index 0, right? If I take one step, then the rest of the board is just the board starting at index 1, right? Going up to, but not including the size of the board, right? Take 2 steps, right? The rest of the board is just the sublist starting at index 2. Remember, sublist doesn't return a new list each time, right? It actually returns the part of the original. It returns a part of that, right? Starting at index 1, right? This one returns the part of that starting at index 2. We're not actually making a new board here. It's the same board every time. It's just we're looking at a different part of the board each time. Okay? Now, what's the cost of moving here or here, right? So the cost of solving this board, well, I can just use my cost method to compute the cost. So that's the leap of faith that you need to make when you write a recursive method. Right? You're going to use the method to solve a smaller version of the problem, even though the current version of the problem hasn't been solved yet. Right? So when you find the smaller version of the problem, you just call the recursive method to solve the problem. Right? So I'm going to call the cost method, find the cost of that board. Okay? And I'm going to call the cost method to compute the cost of the other board, right? The smaller board. So that's the board after taking 1 step. That's the board after taking 2 steps, right? Both of these calls to cost, well, that's going to return an int value, right? So that's the cost of solving the board that's 1 size smaller. That's the cost of solving the board that's 2 sizes smaller. Right? The total cost is just the smaller of those 2 costs. That's the lowest cost. That's the lowest cost move, right? And so then I just add the current square, the cost of the current square to that value, to that result, right? And that's the recursive version. That's the recursive solution to that method, right? Which is much easier than trying to write the iterative version of this method, right? So writing the iterative version of this method is not so simple, right? So writing a single loop or writing a method that loops over all the possibilities, not so easy to do. The recursive solution, once you get your head around recursion, is almost trivial to write. Almost trivial to write. It also kind of looks magical when you look at it. It's sort of surprising that you can solve this problem more or less with that one step there. So there's an example of when you might use sublist. All right. Anybody have any questions about that? If you run it, you can run it. You plug in some boards, try it out, and it does in fact give you the right answer. Anybody have any questions about how that method works? All right. There's a harder version of this problem. So there's a few harder versions of this problem. So number 1, so it's great that I can get the lowest cost, but it would be nice if I could also get back the list of moves. Right. So I want to know what moves do I need to make in order to generate the lowest cost solution. Right. So that one's quite a bit harder to do. If you try to solve this problem, I recommend using a method having that signature there. Right. So that list moves, that's going to be your list of moves that's returned back to. That's so when you call the method the first time, this will be empty. Right. The recursive method will fill in this list. Right. So for example, if you gave it this board, then your recursive method should eventually end up setting that list to 1, 2, 2. Right, take 1 step, then 2 steps, and then 2 steps. It should return the lowest cost, right? So it should return 3 plus 6 was 10. Now, there's the jump it problem is relatively simple to solve, right? Because it has a couple of nice properties. So property number one, right? It's impossible to move to the same square twice, right? Because you can't take a step of size 0, right? And you can't take a step left, right? So if you end up, if you could move left, right, for whatever reason, then you run into a problem where you can end up getting stuck in a cycle, right? So you move left 1 square, and then you move right 1 square, and then you move left 1 square, and then you move right 1 square, and so on and so on and so on, right? So that would complicate things, right? Furthermore, the rule of the game makes it impossible to move off of the board, right? So there's no way to jump off the end of the board, for example, right? Now, I can take away those two properties and make another, and create another game. Okay. So here's a variation on jump it. You're given a list of non-negative integer values where the right-hand square is always 0, right? So that's everything else is non-negative, right? So everything else is positive, right? I guess you can have a 0 somewhere in the list, but that doesn't make sense. Okay, starting from the first element, so starting from here, I want to reach the right-hand side of the board, right? Now, the reason you can't have a 0 here is because the number that's in the square, that's the number of positions you can move. And now you can move left or right. You are not allowed to move outside the bounds of the list. So for example, if I end up on the 3, I can't move left 3 squares, right? Because otherwise I'd end up over here somewhere, right? If I end up at the 9, I cannot move to the 0 because I would end up out here somewhere. So now, how do you solve this problem? So for this particular board, right, there's a 2 here. So my only choice is to move 2 to the right to land on the 4, right? I can't move to the left, so I have to go 4 right. So now I'm at the 1. Now I have a choice. I can go to the 2 or the 6, right? And you can see from at this point, it's not at all obvious which direction you're going to go in. Here I'm going to try 6, right? I can't go to the right 6 spaces, so I have to go left, right? I'm at the 3. I can't go left 3 spaces, so I have to go right. Right? I can't go to the left 5 spaces, so I have to go this way. But that's good because that takes me to the answer, right, to the final position. Now that's not the only solution on this board, right? I can go to the 4, then to the 1. Now before we went to the 6, but I can also go to the 2. I go to the 2. Right? Now we know if we end up at the 6, there is a solution, right? So you could in fact go to the 6 and then solve the board. So that's solution number 3. Right? But instead, I can go to the 2, then the 3, then the 5, then the 0. Back here, right? Here, when I have the 2, right, I can go left to the 2. Right? When I get to this 2, I can actually go back to the 2 again. Right? So that's a problem because you can end up bouncing back and forth. Right? In your solution, you have to have some mechanism to prevent you from bouncing back and forth from these 2 positions. So it's possible to find what are called cycles, right, where a move takes you back to a square that you've already visited. And that's what we need to avoid, right, in our solution. And of course, if you have a cycle in your board, you can easily make a board where no solution exists. So that's another problem. You can be given a board where there is no solution. And so however you solve this problem, you need some way to return back to the caller that there is in fact no solution. And so here's a board. It doesn't matter what you do. It eventually forces you into a cycle. You eventually end up on this 1, no matter what you do, right? And so if you end up on that 1, right, then you're forced into one of these 2 squares here. And you've been on one of those 2 squares before. So you end up in a cycle in this case, right? And you don't need cycles to create a board where no solution exists. Right, here's a trivial example of a board where no solution exists because you end up on a square. You're forced to a square that can't possibly take you, where the move forces you off the board. Right? So it's possible to create a board without a cycle where there's no solution. Now, if you want to solve this problem using recursion, you have to remember, right, when you write a recursive method, the size of the problem has to get smaller at every step. Otherwise, there's no guarantee that your solution that you ever reach a solution, right? And in this particular case, it's not exactly obvious how your board gets smaller every time, right? In Jump It, it was obvious, right? In Jump It, you always used sublist to get a smaller version of the board, right? So because you're using sublist, and you're always making, because you're using sublist and you're not passing in 0 for the first number every time, you know that the board is getting smaller every time, right? So in this case, how does the board get smaller, and how do we indicate that the board is in fact getting smaller? Well, the board gets smaller because every time you take a step to a square, you never want to go back to that square, right? So in other words, you want to rule that square out from any possible solution starting from that square, right? So the board does in fact get smaller, right? You eliminate one square every time you move, right? Because you never want to go back to that square, right? Now, how do we indicate that the board is getting smaller, right? So you can't remove the square from the board, right? So you can't use the remove method to remove that square, because if you did, that changes the board, right? So remember, remove removes the element and then shuffles all the other elements back to fill in the empty space. So you can't use remove, so you need to do something else, right? So what we're going to do, do I tell you where? No, okay. So what we're going to do is we're going to change the board, right? So when you step on the square, you're going to change its value to some value that indicates you've been there already, right? Now our board always has positive, non-negative values in it. So every time I step on a square, I'm going to set the value of that square to -1, right? And that indicates that we've been on that square. Okay. So what about, now here, instead of defining the base cases, I'm going to define the recursive cases first. So the recursive cases are actually fairly straightforward, right? So I'm on a square somewhere on the board, right? You know that the solution is obtained either by moving left or by moving right, right? So your recursive cases are, can you move left without falling off the board, right? So can I move left without falling off? If so, can we solve the board by moving to the left, right? So here you just call, so if you can move left, you move left, and then you recursively call the method to solve the board starting at the new square that you moved to. Right? But you have to remember, you can also move right, right? So if you can move right without falling off the board, right, can the board be solved by moving to the right? Again, you're going to call your method recursively to solve that problem there. Right? So here I'm going to write the following method. So my method's called isSolvable, right? It's going to take in a board. Right? We're going to start at this index, right? So I want to know, is this board solvable starting from this index, right? So to solve the initial board, you're going to pass in 0 for the index. At every other step during the recursion, this value will be some other value. If you get back to index 0, you know you have a problem, right? Because you've gone back to the beginning of the board. It's going to return true if the board is solvable starting at that index. It'll return false if the board is not solvable when you start at that index, right? The method does not permanently modify the board, right? So when you write a method, right, in any programming language, a method or a function, right, that takes in some piece of information that the caller is giving you, right? If it's possible at all, you want to avoid modifying the information that the caller is passing you, right? So in other words, you want to minimize the number of side effects that your function or method has, right? Because anybody who's calling this method, they might not want their board to be all messed up, right? So you can imagine if this method does something strange to them. So our method's going to set the values to -1, right? Board values to -1. When you give it back the board to the caller doesn't want to see all these -1s in it, right? They want back their original board. right? Otherwise, they have to pass you a copy of the board, and that becomes really inconvenient for the caller, right? So whatever I do to the board, I'm going to have to undo. Otherwise, that's not true. Okay, so I'm going to do the base cases later. Actually, it's 17 after the hour. So before I give you the, well, you can look at the solution in the slides if you want to. But I'm going to stop it here so I don't want to get halfway through a recursive method and then come back to it later. So I'll stop the lecture here and we'll finish this up at the end, at the beginning of the next lecture. And then we'll talk about sets and maybe maps in the next lecture. All right. Anybody? Well, we have, yes, you will have 10 labs. There will be another lab coming up today, and the third one will come out later this week. It's just because I've been behind because of the deferred exams. For the assignment, is it fine if we just copy and paste the error handling into each method, or should? Oh, no. Oh, yeah, yes. So that's a good question. Obviously the ideal way to do this is to create a separate method that does any code that you might be repeating. Right, so that's what we'd really like to see. For this assignment, you're not going to lose any marks if you repeat the error checking code. Right, the purpose of this this assignment is to get you writing exceptions. Right, is to get you used to validating inputs and throwing exceptions because that's not what you do in C. Right, so if you copy and paste, that's fine for this assignment. But if you want to make a method, a separate validation method, that's great as well. Right? And in fact, that would be the way you would do it in a professional environment. Could you explain how you want us to submit the assignment? I'm a little confused. You just submit your source code, Anders. Right? So you. So I guess step number one is you need to find your source code, right? Okay. So here. Right, and then you you just submit your Java file. So look, suppose you wanted to submit coinflip.java, right? So step number one is you need to figure out where on earth is your file on your file system. Okay? So one way to do that is to sorry, come here. There. Okay. So step number one. If you know where you created your project, your Eclipse project, then you can just go there, right? So I happen to know that this is in document blah blah, right? It's in my CMPE 212 directory, right? I know it's in my workspace directory, right? This is project CMPE 212. Well, yours will be assignment 1. So here, I'm just going to go into assignment 1. Right now, whatever you do not go into the bin folder. All right. Go into the SRC folder, right? Go into the A1 folder, and there's your sandpile.java file. So that's the one you want to submit. So you just you submit that file on Onq, right?
Sorry, Professor. So when I tried to do that, Onq rendered it to a text file.
It doesn't matter. I mean, did it change the extension? It shouldn't have changed the extension.
It said it was it was sandpile.java, but when I tried to open it to see what it looked like, it was it was a text file.
Yeah, it should be a text file. Right? Okay. This is a text file, right?
Yeah. I just didn't know if you want it to be like a Java file, like a jar file.
Oh no! Don't submit a jar file or a class file. Submit the .java file.
Okay, thank you.
Yeah, absolutely. Submit the .java file. If you submit anything else, we can't mark it because we can't see your code, right? Okay. Hopefully that clears things up. Any other questions? All right, super. See you Wednesday.